Hello everyone, welcome to this video. Let me introduce myself. My name is Regina Mutiara Winokan, with NIM 2 System Information Class B 110600056. In our modern, hyper-connected world, we are constantly moving through invisible structures. Whether you're browsing the internet, traveling across a city, or simply checking your social media feed, you are interacting with a branch of mathematics called graph theory. But what exactly is it? At its simplest level, graph theory is the study of relationships. It provides a universal language to describe how things, any things, are connected to one another. Today we're going to look under the hood of the digital age to see how these webs actually work. To understand a graph, you only need to know two terms: vertices and edges. Think of a vertex or a node as a point of data. This could be a person, a computer server, or even a landmark on a map. An edge is the line that connects them, representing a relationship. For example, if two nodes are people, the edge between them represents their friendship. If the nodes are cities, the edge is the highway connecting them. By mapping these simple components, we can visualize incredibly complex systems, from the neural pathways in your brain to the global flight paths of every airline in the world. Not all connections are created equal. In a directed graph or a digraph, the relationship goes one way. Think of a one-way street or a Twitter follow. Just because you follow a celebrity doesn't mean they follow you back. In contrast, an undirected graph represents a mutual connection, like a LinkedIn link or a two-way road. But here's where it gets powerful: weighted graphs. In these models, we assign a numerical value, a weight, to every edge. This weight could represent the physical distance between cities, the financial cost of a transaction, or the time it takes for data to travel. By adding weight, a simple diagram becomes a high-powered tool for optimization and decision-making. The most famous application of this is the shortest path problem. When you ask your GPS for directions, it uses an algorithm, most famously Dijkstra's algorithm, to scan a weighted graph of the city. It treats every intersection as a node and every street as an edge. By calculating the lowest cumulative weight, factoring in distance, speed limits, and real-time traffic, it identifies the most efficient route among millions of possibilities. This same logic is used by internet routers to send your emails through the fastest series of servers across the globe. Graph theory also solves logistical nightmares through graph coloring. The rule is simple: no two connected nodes can have the same color. This isn't just for art, it's for efficiency. Mobile network providers use this to assign frequencies to cell towers so that overlapping signals don't interfere. Schools use it to create exam schedules. If two classes have the same students, they are connected by an edge and must be colored with different time slots to avoid a conflict. It is the ultimate tool for avoiding interference in a crowded world. As we look to the future, graph theory is helping us map the human genome, stop the spread of pandemics, and even detect financial fraud. It proves that the most important thing about an object isn't just what it is, but how it relates to everything else. In a world that never stops connecting, graph theory is the map that shows us the way. Thank you for listening.